Recently, my colleague Pat Ryan spoke with Dr. John Charles, the Associate Manager for the International Science in NASA's Human Research Program, about the science plan for expeditions 43 through 46, and asked him to identify the greatest concerns we have about how prolonged weightlessness affects a person.
The way weightlessness affects people after long periods in space is part of the problem, and the rest of the problem, of course, is isolation and distance and things like that from family and support. But the weightless problems are I think, very interesting, and they concern loss of bone mass, that is, the loss of bone structure and integrity, because the bones are no longer hefting around our bodies and under 1G. The muscles that make those bones move also get weaker. The cardiovascular system, which doesn't have to pump blood from the lower body into the upper part of the body because of pooling because of gravity, also has certain changes, not so much in the force of the pumping, but in the distribution of the fluids in the body. The vestibular system, the sensory motor system, which is acutely sensitive to the effects of gravity, of course, notices right away that weightlessness doesn't happen anymore, or weightlessness happens and gravity doesn't happen anymore. All of these changes occur fairly quickly in flight, but we're now looking at the long-term manifestations of these very, very physical changes, along with the psychological aspects and other aspects of just being in a confined environment and at great distance from support and so forth.
Do we anticipate that all of these bad effects get worse the longer that you stay? Would it be worse in month 7 or 8 than it is in 2 or 3?
Well, we're doing this one-year mission, and that the goal is to try and answer exactly that question. We have always in the life sciences assumed that the next increment of duration is where the cliff is where the brick wall is that we're going to run into. And so far, we've really not seen it. So far, the human body has proved remarkably adaptable to the most novel environmental situation that is possible to conceive of, and that is the absence of gravity. Gravity has influenced everything on the Earth in terms of biology from the very beginning of biological time.
Right.
And now we're finding that those resources that the body has to take care of itself in different attitudes, different postures, different environments on the ground are also pretty good for living in the absence of gravity, as long as you maintain pressure and temperature and food and things like that. So we are not yet encountering the cliff. There's no here be dragons on the map that we've encountered so far. We're finding that many of the changes that occur in the human body physiologically occur fairly soon, that is within days, weeks, even months of time and weightlessness. But after 3 or 4 or 5 months, our bodies would be pretty well accommodated to weightlessness as far as we know. Now, that's a big caveat because we don't have many other data points beyond those first few months. But things seem to level off, and we seem to be approaching something that some people call a space normal state. That is, you're through the turmoil and the uproar of the adaptation and the accommodation process. But there's always the what if. If we're talking about 2.5-year round trips to Mars, all of it in gravity less than Earth's gravity, weightlessness for the transits out and back, and 1/3 of a G while you're on the planet of Mars, wouldn't it be nice to know ahead of time before you embark on those missions whether there is a bugaboo out there that's gravity related? So we're gradually expanding the flight durations. The space station has given us a huge database on roughly 6-month durations, and so far, like I say, not many bugaboos, but there was one, and that is the visual problem that people have heard about before, which seems to have manifested itself along about month 3 or 4 or 5 in these 6-month missions. And it was a bit of a surprise because people had not really reported that degree of visual change previously. Now the Human Research Program is trying to understand what is unique about the current situation, about the crew members, about the environment, about whatever else may be causing a visual change, so we can understand that problem, and also so we can generalize to other problems. What other problems have we missed that will manifest themselves on, say, month 13 or month 20 of a long duration flight? We're trying to avoid those problems.
On this mission for Kelly and Kornienko, how do you take data about what's happening to them in order to study later and learn what you need to learn?
We use all the techniques available in 21st century medicine, including nowadays genetic analysis. You've heard of the twin study that Craig Kundrop, my colleague, talked to you about recently. That is really an application of individualized 21st century medicine to understand the effects of long-term spaceflight on very specific individuals. But we also use the other techniques that many of us are familiar with from visits to the doctor's office, the blood pressure, the ECG, the stress testing. We have treadmills and other ways to stress test individuals in flight. We have blood draws. Nobody can forget the blood draws. The astronaut's absolutely the most favorite activity to do is to be punctured and have blood drawn in flight. And those are going to be really well springs of new and valuable information on the effects of long duration flights on these two crew members doing the 1-year mission, but they will allow us to form a commonality with a large 6-month database. We also have, but wait, there's more. We also have a large set of psychological and psychosocial investigations, because the Human Research Program considers the psychological, psychosocial aspects of long-duration flights off beyond Earth's orbit and off to Mars as some of the most significant, the most profound potential problems that we might encounter. And the funny thing about the psychological changes that may occur in flight is that you don't have them until suddenly you've got them in a big way. So the trick is to develop techniques that will monitor crew members' psychological states and their ability to form teams and their ability to sleep, which is an important contributor to psychological health. And then using those techniques that we may have developed on the ground and in isolation studies, apply those to long-duration missions to validate them in the actual flight environment.
But part of the study now is to find out just exactly what they're capable of doing when they do return to Earth at the end of the year.
Yes, Pat, the goal of that investigation, which is called field test, is to understand the capabilities of astronauts immediately after landing from a long duration period in spaceflight, which would mimic the transit time from the Earth to Mars, to allow us to help the spacecraft designers for future Mars vehicles understand what they have to build into the landing vehicle and how much they can expect the astronauts to do immediately after landing. This is a very exciting and actually a very, I want to say, popular. It's enthusiastically supported by the crew members, the astronaut office, as well as the scientific community, because it's a good demonstration of what people can do immediately after landing, and it has operational and scientific benefits.
And I think it's also interesting to note that in this case, in the 1-year crew, a lot of these investigations are joint work by American and Russian scientists in ways that hadn't happened on this project up to now.
That's exactly right. In fact, these were two separate ideas that were promoted by all of the space station program managers, the U.S., Russian, European, Japanese, Canadian. They said, we would like to understand what happens on a 1-year mission, and we'd also like to see more joint activities between the partners, taking advantage of the resources that each brings to the space station, and breaking down any artificial barriers between the modules so we can move hardware back and forth, crew members back and forth, take advantage of equipment that's in one and crew members that are in the other, and so forth. We quickly melded those two efforts into one, so the 1-year mission and the breaking down barriers became the same activity, and we're using this 1-year mission as a highly visible demonstration of how to do that. Once we get these techniques, these lessons learned, figured out, we hope to be doing this on every ISS mission beyond the 1-year mission, so that we take advantage, as I say, of the resources everybody brings and provide benefits to all the partners.
It'll be very exciting to see how it goes. Yeah. Thank you for letting us get a look into what's going to happen soon.
Delighted, Pat.
John Charles is with NASA's Human Research Program.